Hi, I'm Joe.
I'm Deanna.
Hi, I'm Megan, and we're the Lockheed Martin team. The goal of our project is to improve the mechanical properties of the additively manufactured alloy ALSI 10Mg through heat treatments. Additive manufacturing is just like baking a cake. In a cake, when you stack sheets of cake bound together by icing, you build and form the entire cake. You do the same thing in additive manufacturing. The difference is, instead of using cake and icing, you are using fine powdered metals and heat. In direct laser metal sintering, a laser is used to heat the metal particles, binding them together in a controlled pattern before more powder is added and heated to form another layer, just like how a cake is made. ALSI 10Mg is an alternative to the more traditional AL6061, which does not have the properties conducive to an additive manufacturing process. The team's goal is to improve the yield strength, ultimate tensile strength, and ductility of the ALSI 10Mg alloy so that it meets the mechanical property requirements for Lockheed Martin and can be used in current and future products.
Each of these properties can be related to how silly putty can be stretched and pulled. Think of yield strength as how far you can pull the silly putty until it starts to deform. Ultimate tensile strength is how hard you need to pull in order to break it. And ductility, also known as elongation at fracture, is how far the silly putty can be stretched before it breaks in the center. These three properties are of incredible importance when evaluating a material's performance. The specific values that the team worked to achieve for DMLS aluminum silicon 10 magnesium were a yield strength of 30,000 psi, an ultimate tensile strength of 50,000 psi, and elongation at fracture of 10 to 15%. These mechanical properties were selected as they are very similar to those of the widely used aluminum 6061. The outcome of the project was limited by several constraints, with the main one noted as sample availability. Our samples were directly provided by Lockheed Martin, therefore we could not begin testing until the samples arrived, and our testing was limited to the number of samples that we received. Also, each sample was initially heat treated, followed by machining, which added to the total time per sample needed to obtain results. More recently, the COVID-19 pandemic has unfortunately limited our lab time, which prevented us from completing some of the testing and analysis methods that we had originally planned to use. The team's approach was to subject the samples to various heat treatment times and temperatures to determine which combination will result in the most optimal mechanical properties. By building upon the work done by previous teams, we were able to quickly narrow down the ideal time and temperature window for the desired mechanical properties.
By subjecting the samples to various times and temperatures, we can change the mechanical properties that the material has. This can be similar to how changing the time and temperature at which you bake a batch of cookies can result in a soft and gooey cookie or a hard and brittle cookie. Through our experimentation, we were able to determine that 4 minutes at 530 degrees Celsius is the most consistent and ideal temperature for heat treating this material. This resulted in a mean UTS of approximately 51,800 psi, a yield strength of 32,200 psi, and a percent elongation at fracture of 9.1% for the Z-print orientation. For the XY axis, these values were 49,400 psi, 33,200 psi, and 13.8% respectively. All of these values are at or very near the desired results provided by Lockheed Martin and show significant promise when compared to other published results. Further experimentation is required to determine if the short time and high temperature results in any sort of hardness or microstructure gradient throughout the part, which could result in less ideal mechanical properties. This, in conjunction with slightly longer times and lower temperatures, could result in a more uniform treatment of parts of various shapes and sizes. In addition, TEM analysis of the samples to determine the effect of heat treatment on the microstructure of the material would provide significant insight.